All right, thank you all for coming. So I'll tell you a little bit about some of my research, which is on knot theory. And this particular project is joined with a few people, and they are written in alphabetical order. In pure maths, when you publish, everybody's listed in alphabetical order, regardless of how old they are and what exactly they did for the project and all that. So Hans Boden is a professor at McMaster University, which is a university in Canada, and I started collaborating with him last year. I met him at a conference in 2019, and we had a chat and decided that we wanted to think about this question, and he planned to come visit in 2020, and obviously he didn't. So he did come in 2022. And we started this stuff, and very luckily, at the same time, Damian was starting his honors thesis, and Tilda Wilkinson was starting to do a Dalyell project, and so Damian and Tilda have been very active in this whole area, and in particular, Damian has really ran with it, and I'll comment a little bit on what he's done, but he's done a lot. So this is mostly just me talking about what all these other wonderful people do. So if you haven't seen knot theory before, just wanted to give you a quick intro to what sort of questions we think about. So what is a knot? Here is a knot. Right, this is something that you might do when you tie your shoes, hopefully. But mathematically speaking, that's not a very interesting knot, because if your shoelaces are this long, then any knot you tie in your shoelaces, I can carefully pull out the end all the way through the knot and undo any knotting that was done. And so in a mathematical sense, all knots on a short shoelace are nothing, they can just be undone. So there's no knots on a short shoelace. In the mathematical sense. The way that we might get knots that are mathematically interesting is to either make the string super long. So mathematically we think of it as infinite. But in practice, it might just be super long, like a string of DNA or something that is compared to his width, super long. And so if you have a little knotting on it in the middle, the ends are very unlikely to slip out. Or you can make it a circle. And these two ways are kind of equivalent, but I'm gonna think about it the circle way, and that also has some biological and other practical applications. Thinking of it as a circle, mathematically it's almost the same thing. If you just have one loop, then it's exactly the same thing. So the big question of knot theory, which is deceptively simple but not so simple to answer, is how do you tell if two different looking knots are actually the same knot? So here's the knot that I've drawn up there, just drawing it kind of nicer on a circle. Here's another knot. Are these two knots the same? So if you think about it a little bit, you can kind of see how you can take this whole arc of the string and move it over down to the left, and then it kind of comes here, and then it sort of becomes, if you extend this little loop a little bit, jiggle it a bit, then it becomes that other knot. So these two knots are the same knot, bit of maybe second-year linear algebra. When I say same, I mean there's an equivalence relation on knots, and that equivalence relation is specifically defined in topology. It's called ambient isotopy, but I will not go into that. So when I say same, I mean one can be moved around without tearing the string to look like the other. So that was easy enough. We got two knots, we stared at the commit, we saw that we can jiggle one of them to look exactly like the other. But what if I have two knots and I keep staring at it and I don't see any way to make them look exactly like each other? Then how will I ever know that two knots are not the same, right? If I keep doing that, I keep staring at it for 15 years and I can't see a way to make one look like the other, maybe the next day Alicia will come and she's just like a knot genius, and she will look at it and say, here's a way that you didn't come up with, and they are the same after all. So how will we ever tell? And for doing that, there's a very clever method, which is called the knot invariant. So what's a knot invariant? It's something into which you can feed a knot. Now, for the most part, you feed a knot means you take a picture of the knot, whatever picture, like if the same knot could have many, many different pictures depending on how you take the picture. Like that one and that one are pictures of the same knot. But you take a picture of a knot, and if you look at that picture, that's something that you could feed into a computer. Because it has those places where one strand goes over the other, those are called crossings. And you can just like list the crossings, like crossing 1, crossing 2, crossing 3. Each crossing has 4 ends, and then you tell the computer, oh, that was a bad idea. There's a tool. So, crossing, crossing, crossing. Each crossing has 4 ends, 1, 2, 3, 4. And you tell the computer how those ends connect to each other. And that's like a way to basically encode what the knot is. So we can encode the knot diagram and we feed it into this machine. So let's say that one. And then there's like, I don't know, some sort of machine. Okay, I feed into it the knot diagram, and out of it comes something like x minus 1 plus x inverse. Okay, so I feed the knot diagram into the machine, and the machine says x minus 1 plus x inverse. And it's a knot invariant, the machine is a knot invariant if it has the clever property that if I feed into it the same knot, it will always give me the same answer. So even if I fed into it that other picture, which on the face of it looks different, it's a picture of the same knot, and so the knot invariant will give me the same answer. Even if the picture looks different. So that's the key thing that a knot invariant does. And why is that cool? It's very cool because this means that if I feed into the machine two different knots, then it will give me two different answers, which I can compare because the answer is something like a number, a polynomial, or something that I can identify as same or different. And if it is different, then those two knots that I started with could not possibly be the same. So there's no risk that Alicia will come around the next day and say, look, I found a way to make one of them look like the other, because it's not possible. Once I fed it into the knot invariant and it told me that they belong, that they give different answers, then I know that they are definitely different. So here's an example. This machine that I drew is called the Alexander polynomial. And I already told you that the Alexander polynomial of this knot, which is called the trefoil knot, is x minus 1 plus x inverse. And the Alexander polynomial of this other knot, which is called the figure 8 knot, and you'll soon discover that I'm actually really bad at drawing knots. But this went well. So that is x minus 3 plus x inverse. So x minus 1 plus x inverse is not the same polynomial as x minus 3 plus x inverse, and so these are different polynomials, and so those knots are different. Okay, so the Alexander polynomial helped us tell those knots apart. No, for sure, definitely, nobody ever will find a way to make that top one look like the bottom one. Now, that's great, but it doesn't necessarily work, right? An invariant, if I feed it different knots, nobody has promised that it gives me different answers. So some invariants are better than others at this. Some are really good at telling different knots apart, and some are just so-so. And there's a trade-off. So the Alexander polynomial is actually not super good at telling different knots apart. There's lots of pairs of different knots for which the Alexander polynomial is the same polynomial. However, the Alexander polynomial is easy to compute. So it's computable in n cubed time, where the number of crossings is n. Oh, my first job was much better. I just happened to catch a really good one. So it's not great at telling different knots apart. fast to compute. Now what about, do we have better invariants? In particular, you might ask, do we have any invariants which are absolutely killing it? Meaning that if I feed it two different knots, it will definitely give me two different answers. So I can use that invariant to tell any two knots apart for sure. So feed two knots into the invariant. If the answer is the same, those two knots are the same. If the answer is different, those two knots are different. No further questions. Are there any such invariants? So an invariant like that is called a complete invariant. So it's not only same knots mean same answer, but also different knots mean different answer. So if you've done a little bit of algebra, or in fact just a little bit of analysis also, this means an injectivity property, right? Same knot means same answer means it is a well-defined invariant, it's a well-defined function on the equivalence classes of knots. And different knots mean different answer means it's an injective function on the equivalence classes of knots. Do we have such invariants? The answer is yes. But they are not awfully easy to compute. So any complete invariant is almost by definition very hard to compute. So very long and hard to compute and to compare the answer. Right, so computing and comparing the answer are both necessary. So with the Alexander polynomial, the answer would be a polynomial. And I can easily compare polynomials to each other. On the other hand, for the complete invariant, so one example of a complete invariant is what's called the knot group plus peripheral system. So if you've done a little bit of group theory in some unit or another, then you know what a group is. So the knot group is a group associated to a knot, and you basically get it, the elements are some equivalence classes of loops where you take your knot, you remove it from space, so you have like space minus a knot. It's like there's a little tunnel going around in space that you like bump into and you can't go through. And then you do loops in that space, and based on how those loops go, those are the elements of your group. And there's some group operation where you compose loops or concatenate loops. It sounds kind of crazy, but it does work. It gives you a group. And then you put some extra information next to that group, and that gives you a complete invariant. But if I give you two groups, it's not so easy to tell whether they are the same group, whether they are isomorphic. If you've seen even a tiny bit of group theory in, say, Math 2922, you know that that's a hard question. So not so easy as comparing polynomials. So there's lots of disadvantages to that invariant from a practical perspective. So I would like to tell you about a sort of nice class of knots. So if we restrict to our attention to what's called alternating knots, then this question becomes a whole lot more manageable than telling all possible knots apart. knot diagram or knot picture is alternating if it goes, like if the crossings go over, then under, then over, then under, then so on. So if it alternates over and under. And all of the examples that we've seen so far are alternating knot diagrams. So you see here, if we come around this knot, we go over a strand, then we go under here, then we go over, come down, we go under, over, under, and then back to the start, over. Okay, so it goes over, under, over, under. This one too, we go over, under, over, under, over, under, over, under, and around. So those are both alternating knot diagrams. And they are called the trefoil and the figure eight. And a knot is alternating if it has a picture which is alternating, if it has a diagram which is alternating. So it might be that I can write a knot alternating diagram for a knot, like if I jiggle it around, it will not be alternating. For example, like here, if I took this strand and just pulled it over this whole part, then it would go over, 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 over. It would not be alternating. But this knot is still alternating because there is a picture of it, there exists a picture of it which is alternating. So a knot is alternating if there exists an alternating diagram or picture for it. And I'll show you what's the smallest non-alternating knot. It has 8 crossings, and this is like the biggest drawing challenge that I've ever done in a lecture. Okay, so we'll go over that and make sure it's alternating. So from here, I come over, oops, then under, then over, then under, up. I was over, right? Under. So over, under, over, under, over, under, over, under, over, under, over, under. Okay, so that's the smallest, so least crossing number, like least number of crossings, non-alternating knot. I'm sure you can do a least number of crossings alternating knot diagram, but that would be an alternating knot, because for the same knot you could find some other diagram which is alternating. This is the smallest non-alternating knot. So for this knot, there's no diagram at all which would be alternating. Okay, so what I'd like to show you is a way to come up with, to construct an almost complete invariant for alternating knots, which is also pretty nice to compute. In fact, Damian has computed it, and reasonable to compare. not necessarily completely trivial to compare, but there's reasonable comparability also. And let's see. So it depends on a really cool sort of correspondence between knot diagrams, alternating knot diagrams, and planar graphs. Who here knows what a graph is? Hands up if you know what a graph is. A few people. Okay, so graph is just points connected by lines. The points are called vertices, the lines are called edges. And the graph is planar if the lines don't cross each other. So here's how you do it. Take an alternating knot diagram. And you see that this divides the plane into some regions, right? There's some like faces here and here and here and here, and there's one outside. So what I want you to do is to checkerboard shade those regions. So by checkerboard shade, I mean just like on a checkerboard, if I shade in one region, then anything that shares a boundary with it, like an edge with it, it should not be shaded, right? There's no two black squares next to each other. So if I shade this one, then I shouldn't shade this one, shouldn't shade this one, shouldn't shade the outside one, but I should do this one. Because ones that are next to each other should not be both shaded nor both unshaded. So that's called checkerboard shading. And then put a vertex in each of the shaded regions. And then those shaded regions connect to each other via the crossings, right? It's almost like there's like a little band twist around those crossings. So across each of the crossings, I'm going to put an edge. And we also like to keep track of which crossing is which. So that is a graph with 2 vertices and 3 edges, and those edges are called 1, 2, and 3. Okay, so from a knot you can get a planar graph, and the fun part is that you can also go back. So from a planar graph, you can put a little crossing on each of the edges and then connect along the regions, and you get back the alternating knot. Now, the reason this makes sense for alternating knots and not necessarily for all knots is because if I was doing all knots, then I would have to decide for each edge which one goes over and which one goes under, and that will give me lots of different knots. Whereas for alternating, I just have to make sure that it goes over, under, and so on, and so it all gets determined. So you can go from alternating knots to planar graphs and back. And the invariant works in the following way. So you take an alternating knot, okay, and then to it you assign this Tait graph, which I call TK. Sorry, TK. And then to that, we assign what's called the lattice of integer flows. which I will call f of gk, and this is the invariant. And in a twice as long version of this talk, I will tell you what it is, but I think in this talk I will not. So let me just tell you in a couple of words what it is. It's, for you who know what that means, it's an abelian group which consists of cycles of the graph. So the elements are cycles in GK. So a cycle in GK is like, you know, going along edge 2 and then along edge 3 so that you make a circle. And it also has an inner product, which is a bilinear map from f of gk cross f of gk. So that's a Cartesian product, or like direct product, to f of gk. Okay, so that's some stuff, some algebra comes out. So it's a bit more complicated than the Alexander polynomial, because you don't get just a polynomial, you get some more complicated creature, but it's still like a reasonably manageable creature. Abelian groups are not as bad as groups. So that's the invariant. And it turns out that this is an extremely good invariant of alternating knots. It nearly completely distinguishes them. So if you have two alternating knots, if you have two alternating knots, you feed it into this machine, you will get, if the knots were different, then you will get different answers. And I'm lying a little bit. It actually doesn't distinguish knots which are so-called mutants. That's why I said almost. But it's, nonetheless, it's very hard. So the last thing that I wanted to tell you about in just like a couple minutes at the end, I know the pizza it smells good, so we don't want to be too long, is what happens if you're looking at knots that are not like in sort of three-dimensional space and like the pictures are on a plane, but rather they are in a more complicated, what's called a manifold. So it's like a three-dimensional space, but with more, you know, it's a three-dimensional manifold compares to three-dimensional space, like a donut compares to a sphere or a flip. So it's a more complicated three-dimensional space. What if the picture of the knot is on a different surface, like on a donut? So there's various reasons why people are interested in these, coming from you know, other areas of mathematics and physics. But if we just accept as people who like topology that donuts are like inherently interesting, then it's a totally reasonable question. If my knot picture is drawn on a donut, so I will draw a knot on a donut. When I do the back thing that's on the back of the donut, okay, this is a knot on a donut. Can I play the same game? It's an alternating knot on a donut because it goes over, under, over, under, over, under, and then back over. So alternating knot on a donut, can I make the same invariant? And this is something that nobody had done before Damian and Tilda and Hans and myself. So this is a new question. And it turns out, yes, you can make the same invariant because you can checkerboard shape, no problem. it's kind of funny, this region, like it goes to the back and comes back to the front and all the way here. So it's really like this part and this part, this whole part is just one region. And then I can do the Tait graphing, like I put a vertex in here, I put a vertex in here, and then I'm supposed to come across each of the crossings. So I'll have an edge over here, and then across this crossing I'll have an edge, and I have to find the vertex. How do I find the vertex? I come down to the back and down, and that's the vertex. And then also here, I have to come down and up, and then back to the vertex. Okay, so that's the Tait graph, and it's also drawn on the donut. But I can draw it in the plane, it's fine. So it's just two vertices, and then one edge connects the two of them. Another edge here, this connects the two of them just in a longer way. And this one, this edge is actually a little loop from the second vertex to itself. So that's the graph. So I can do plot diagram, checkerboard shape, graph, feed it into that big machine that I didn't talk about, and out comes an invariant. And Hans and I Damian and Tilda proved that indeed it's an invariant. So if I feed it the same knot, then I get the same answer. But the big question is it still as good? Is it still essentially complete? If I feed it different knots, then will it give me different answers? And it turns out no, and you can kind of suspect that the answer is no, because here, when I draw the graph like that, when I just draw the graph independent of the surface, I lose a bunch of information. Like, I wouldn't know how to put that graph back on the surface. So that invariant sees what my graph is, but it doesn't see how my graph was drawn on the surface. And that's where it kind of loses out on some of the complexity that's going on here. And Damian's amazing result is that he wrote a computer program which found an example of two knots, K1 and K2, which are different, but have the same invariant. So he proved that it's indeed not complete by showing the counter example. But how could he have possibly done that? How could he have possibly seen that they are different? Simon?
Different invariant?
Yeah. So to tell that they are different, you have to find a better invariant, right? If you don't have a better invariant, we'll never know if this is complete or not. So we found a better invariant, and that came from Hans's earlier work. And Damian was able to also write a program to compute that. So what we actually see is that if you compute this invariant, you get the same answer. But if you compute the souped up invariant, you get different answers. So that's the end. Thank you.